Hello, ladies and gentlemen, and welcome back. Root Beer here, looking at question 7 on the Manitoba Math Contest from 2017. If b and c are odd integers, prove that the quadratic equation x squared plus 2bx plus 2c equals 0 cannot have rational roots. Okay, so I'm looking at a quadratic equation. Immediately I'm thinking quadratic formula, because that always gets the roots. Because I can't factor this. I don't know exactly what b and c are. I know they have to be odd integers, but apart from that, I don't know exactly what they are. Maybe they're negative. Who knows? But I do know quadratic formula always will allow me to express the solutions. It will always let me to express the roots. And if we think even further, quadratic formula has that square root sign. And if we're going to have non-rational roots, that square root sign can't turn out to be an integer. You know, we can't be square rooting a perfect square or something like that. So that's probably a plan of attack here. Okay, so let's copy our equation down. X squared plus 2b x plus 2c. And again, I don't know if b and c, they didn't say they're positive, right? Yeah, they just said they're odd. So actually the plus signs here don't matter. I might say something like, by quadratic formula, we can get the roots. So x is negative, the coefficient of x, plus or minus the square root of 2b all squared minus 4a and then 2c all over 2 times 1, which is the leading coefficient. Okay, well, we can clean some of this up, and we are going to be able to divide by 2 everywhere. So we'll get 4b squared minus 8c all over 2. Let's get rid of that 2 and that 2, and we can divide by 4, because a 4 coming outside through the square root sign becomes a 2. And so this guy will be left with 2. So we'll have x is negative b plus or minus square root of b squared minus 2c. And those are our solutions. Now, this is not rational, or as we typically call them, irrational, exactly when b squared minus 2c is not a perfect square. If it is a perfect square, and I guess technically we should be saying perfect square of a rational number, but since they're integers, I think we will be forgiven there. But b squared minus 2c, not a perfect square. Otherwise, we'd have an integer here, plus or minus an integer here. You'd get an integer for x, not even just a rational number. So, b squared minus 2c is an integer. Okay? Because I guess technically if b squared minus 2c were something like 9 over 25, you could square root that and you'd get 3 over 5, and that would give you a rational answer, but b squared minus 2c will never be rational. Well, I guess technically it is rational in the sense that all integers are rational, but we prefer to point out that it's just an integer. Okay. Now, why did they tell us b and c are odd? We haven't used that information yet. Well, odd numbers, we can just say something like, let b be, odd numbers can all be written in a particular way. So I might say let b be 2 capital B plus 1, c be 2 capital C plus 1. So then b squared minus 2c is going to be 2b plus 1 all squared, plus, minus 2 2c plus 1. And that's going to be 4b squared plus 4b plus 1 minus 4c minus 4, or sorry, minus 2. And this is going to be expressed as 4b squared plus b minus c minus 1. Which has a remainder. Yeah, so the key to this one, if you haven't seen something like this before, is to work with remainders when we divide by 4. It's also called working modulo 4. And if you haven't seen modular arithmetic, that is something to definitely look up. But the nice thing about it is, if I square an even number, that square is always divisible by 4. If I square an odd number, it's not going to be divisible by 4, but it will always leave a remainder when we divide by 4. So this is the fact that we're exploiting, because this number that we now have leaves a remainder of 3 when we divide by 4. So there's no way it's going to be a perfect square. And you could either cite that fact, just say, oh, it leaves a remainder of 3, but any perfect square would have to leave a remainder of 0 or 1. Or if you're unsure of that, we can actually just go ahead and show that. So I'll say has remainder 3 when dividing by 4. Okay, and I'll even show you why this works. But that way I can conclude b squared minus 2c not a perfect square. Therefore, no rational roots, which is what we were asked for. Okay, but why does this work? Well, suppose it were a perfect square. Now, if it is a perfect square, k is odd or even, so I can either write k as 2n plus 1 or as 2n, depending on the case. But then k squared is going to be either 2n plus 1 squared or 2n squared, and then that's going to be 4n squared plus 4n plus 1. Well, this part here is just a multiple of 4, and then we have a remainder of 1 here, or 4n squared, which is 4 times something, and a remainder of 0. So you're never going to get a remainder of 3. And if you felt uncomfortable, of course, add that fact. It didn't take us that long to write it out. But either way, we show b squared minus 2c isn't a perfect square, and that allows us to conclude that there are no rational roots to this expression. Okay, so we did use the fact that b and c were odd there. All right, so that was what, question 7, right? So question 7, I'm going to flip the page in anticipation of our next question, and that will be question number 8, and I will see you guys for that one in the next video.